Imagine trying to predict tomorrow's weather, right? But the only tool you have is just a single photograph of a cloudy sky taken yesterday.
Yeah, I mean, you can see the clouds, sure.
But are they actually moving? Is a
Hmm.
storm rolling in, or is it, just overcast?
Right, you're entirely blind to the context.
Exactly. You just can't predict the future from a static snapshot. So, welcome to the deep dive. Today, we're applying that exact logic to factory floors and process capability.
Which is fascinating, honestly.
It is, because whether you're managing a massive manufacturing plant or you're just curious how companies actually guarantee quality, you need to know this stuff. We're looking at how to hunt down special causes of variation and how to predict exact defect rates using z-scores.
And, doing this in the right order is absolutely critical.
Right.
Because predicting mistakes is impossible if the system you're measuring is inherently chaotic.
Right.
You really must establish process stability first.
Wait, define chaotic for a second, because, any factory floor has variation, right? No two parts are ever going to be perfectly identical down to the atomic level.
Oh, totally.
Right.
True. But variation comes in two distinct flavors. So you have common causes, which are the natural built-in fluctuations of a system.
Like background noise.
Exactly. You can't avoid them. But then you have special causes, and those are unpredictable external factors.
Like what?
Maybe a worn-out cutting tool, a sudden power surge, or, a new operator who hasn't been properly trained yet.
Ah, okay.
You basically cannot mathematically predict anything until you track down the root cause of those special causes and just eliminate them.
Okay, so this goes back to the photograph versus a movie analogy.
Yeah.
A standard histogram is like our photograph.
Yes, perfect analogy.
It shows us the overall spread of sizes or weights, but it totally hides when a special cause hijacked the process.
Which is exactly why engineers rely on the movie version, right?
Yeah.
Run charts or control charts.
Okay.
Think of a scenario where you measure a batch of machined parts, and the histogram looks perfectly symmetrical. It appears, entirely capable.
So you think you're in the clear.
Right. But plotting those exact same measurements chronologically on a run chart tells a completely different story. You might see the process average drifting wildly up and down over time.
Oh.
Yeah, never actually staying centered near the target.
Meaning the operator is just constantly overcorrecting. Or maybe a machine is slowly rattling itself out of alignment.
Exactly. If you only look at the static spread, you're blind to the actual cause. You have to find that specific physical issue.
Like tightening the bolts or training the operator.
Yes, get the process into statistical control. Only then do you have a stable foundation for predictions.
Okay, so let's say we've done the detective work. Our run chart is flat, it's stable, but we still have that inherent natural variation left over,
Those are
right?
common causes, yeah.
How do we mathematically calculate the damage of that normal variation to, predict our actual defect rate?
So this is where you introduce the capability index, or CP, and z-scores.
Okay.
CP essentially measures how well your process spread fits within your acceptable tolerance limits. To find your expected defects, you calculate a z-score, which, in this context, translates to 3 times your CP.
Wait, let me pause you there. Standard deviation covers the whole bell curve, right? Are we just taking a guess based on the middle of our production, or?
No, we're focusing entirely on the extremes.
The edges.
Right, the tail areas of your normal distribution. A z-score evaluates how many standard deviations fit between your process average and the absolute edge of your specification limits.
Oh, I see.
It is literally measuring the distance from your average output to the cliff edge of failure.
So if we're manufacturing U-bolts, we have an upper tolerance limit.
Meaning it can't be too wide.
Right. And a lower tolerance limit, so it can't be too narrow.
Exactly. And because no process perfectly hits the target every single time, some percentage of those U-bolts will inevitably fall off either cliff.
That makes sense.
By evaluating those tail areas, engineers can calculate the exact percentage of U-bolts that are too small and the percentage that are too large. Adding those two specific drop-off zones together gives you the total expected non-conformance rate.
For the entire production run.
Right.
So the strict order of operations for anyone dealing with quality control is this. You absolutely must establish a stable system by eliminating those unpredictable special causes first.
First and foremost, yeah.
Before you can use z-scores to calculate your capability and predict your defect rates, you can't predict your arrival time if the driver is randomly slamming on the brakes.
Or taking unexpected detours. The statistical models rely entirely on the underlying behavior remaining consistent over time.
Right. Well, before we wrap up, there is a fascinating puzzle here.
Oh, yeah.
Even if you lock everything down and have a perfectly centered process with a capability index, a CAP of exactly 1, the math dictates that you will still produce about 2,700 defects for every million parts you make.
It's wild, isn't it? Which raises an incredibly difficult question for management.
Yeah.
If a mathematically capable system still naturally produces thousands of errors, at what point does the cost of chasing a mathematically perfect defect rate
The endless tweaking.
exactly outweigh the cost of simply dealing with the defects themselves?
That's a great question to leave you all with. Think about where that line is for your own projects. Thanks for joining us on this deep dive.